Here we've got a coil which is sitting between two magnets, and these, when it says a time-dependent magnetic field, it means that depending on what the time is, the magnetic field might change. So we're in control of these magnets. We can change the field between here. And we've got a circuit here so we can measure the voltage. And this coil has 120 turns. 10. So they give us what happens to the magnetic field, how it changes. So the magnetic field changes like that, and they want us to sketch a graph of the voltage against time measured by the voltmeter. So really what we want to know is how does the flux change? Because if we've got that, what we can do is we can say EMF, which is the voltage, is equal to negative N change in flux over change in time. And in the last question we did something very similar, which was this thing here, change in flux over change in time, means the gradient of a flux graph. So we need to know, what does a flux graph look like? Well, flux equals B times A. And our area doesn't change in this. They don't say they change it by turning it or changing the shape. Because the area doesn't change, the flux is going to be proportional to B. What does that mean? It means when flux changes, when field changes, flux changes. And simply put, what that means is, if I was to draw a graph of flux versus time, it's exactly the same. Steep, flat, not so steep. This goes up to 1, this is 2, this is 4. So now that we've got our flux graph, we need to take the gradient of this to get our voltage graph. Now, the gradient here is positive, and it's quite steep. The gradient here is 0, and the gradient here is negative. Because there's a negative in our thing that gets from change in flux to voltage, that negative there, this means the value of our voltage at the start is going to be negative, it's going to be 0, and it's going to be positive. Okay, because the negative times the negative gradient, still 0, and negative times negative gradient here is positive. This is really steep, so this is going to be very high here. This is going to be 0 along. Let's do this in another colour. Very high here, 0 here, and this section from 2 to 4 seconds isn't as steep as this first one, so it's not going to be as steep, not as high. That's what our graph's going to look like. Oh, jeepers. It's pretty bad. Cross that out. Alright, next one. Right, another time magnetic flux through these is N, there's a constant flux of that much. Magnetic field is now reduced to 0 over a period of this time. So the magnetic field is reduced to 0, and therefore the flux, the final flux, also goes to 0. And this must be the initial flux. Calculate the EMF, same as before. EMF equals negative N change in flux, change in time, change in flux, change in anything is the final minus initial. In this case, the final magnetic field goes to 0, so the flux is 0, and the initial was this, 3 by 10 to the minus 4 Weber, so the change in flux is minus 3 by 10 to the minus 4 Weber. Let's put in the equation, negative 120 times negative 3 by 10 to the negative 4 over the time, and you work that out, it comes out to 3 volts. Alright, that was number 10. Oh, I've missed a question. My mistake. Number 9 was identify the physical law you use for constructing your graph. So the law we used was EMF equals negative in change in flux over change in time, and that's called Faraday's law. Sorry about that. Alright, last question, number 11. Again, we're looking at this. The field is being reduced. In what direction? From P to Q or Q to P will the current flow through the ammeter? 5 above. Explain your answer. Alright, so situation 1. Let's do it as situation 1 and situation 2. Situation 1. Here is our loop. This is my 3D loop, and you've got field lines going through like that. And as you turn it down and off, situation 2 is that there's going to be much less field lines. Now, Lenz's law that we've always written somewhere that we can cross out later. I like things the way they were. How did I know this was a Lenz's law question? When they ask which direction will current flow, always Lenz's law. The direction of the current for this sort of stuff, Lenz's law. And our translation in our notes is always that I like things the way they were. So how did it like things? It liked having a lot of field lines. And now it doesn't. So what is it going to do? It's going to make its own field lines like that. So let's start writing this out. We'll do the direction last because we worked it out. Lenz's law, and when we write the actual law down, you've got this one in your cheat sheet. So Lenz's law is that a current gives rise to a field to oppose a change in flux. It's actual Lenz's law, and this is the translation. I like things the way they were. I didn't like having a change in flux, so I'm going to make a current to make a field to oppose that because I like things the way they were. So it's going to make a field to the right, according to this picture here, the green one, because it was red. It likes things the way they were. There's hardly any anymore, so it wants to make things the way they were, so it's going to make a field to the right. Makes field to the right. And what the current that made that field is the current. We're going to use our right hand solenoid rule. And if I grip this with my right hand, my thumb, it's right over here, it's pointing this way, and my thumb it's my attempt at a right hand. My thumb points in the direction of the north, which is that way there, points with this arrow, and these follow the current round, which we don't know what it was, but I lined my thumb up first and pointed with this arrow, and the only way I can do that is if I grip this way, so the current must be going this way, which is this way, which is down here, which is along here, which is from back along here, from Q to P. Makes this field is from Q to P. There we go.